So our next topic then after subatomic particles has to do with something called atomic number and atomic mass. These are two very simple ideas that are important in understanding how atoms are compared to each other and how we can distinguish one element from another. Also, when we're looking just at one element, how we can distinguish the different kinds or the different forms of that element from the other forms of that element, at least in terms of mass. There's a little more to it than that as we go further, but for now that'll do. So our two topics then on this video are atomic number and atomic mass, and how we sort of use those pieces of information to identify and tell elements apart. Atomic number is simply the number of protons in an atom. This is a very key identifier for any element. It's as unique to the element as your social security number or your student ID number might be to you. Now, all cases of identity theft aside, in elements, there aren't cases of identity theft. You can't take on the atomic number of a different element without actually becoming that element. And so you can't steal another element's identity as you might if someone got your social security number or your student ID and started racking up your lunch bill or something. Atomic number is equal simply to the number of protons in an atom. So there actually is a meaning to the atomic number. Your social security number, your student ID number probably don't have a lot of specific meaning to you and don't describe anything quantitative necessarily about you. They're sort of randomly assigned. But in the atomic number, the number of protons is what's being described. And that number of protons is the key identifier at the beginning to tell us something about that element. It's found on the periodic table that you'll be getting in class, and hopefully by now have gotten in class, as the large number in the upper left-hand corner, and it's blue on your periodic table. Now, not every periodic table puts the atomic number in the upper left-hand corner. Some of them are in the very top, some are in the very bottom center. They're all over the place. But almost any periodic table out there will list the atomic number and maybe nothing else with the element's symbol and name. But the atomic number is the very key, basic piece of information. If nothing else is given, the atomic number will be given. I used to have a pocket-sized periodic table. It was the size of a driver's license that I kept in my wallet. Yes, insert your own jokes about my nerdiness here. But I used to have a pocket-sized periodic table that I believe listed nothing more than the element's name, symbol, atomic number, and I think maybe atomic mass, average atomic mass, which we'll be getting to later. But just really key, simple information that can tell you a lot and help you to do a lot of different things in chemistry with just that stuff in mind. On this example diagram or image here, you see platinum. This is scanned right off of our periodic table. And in the upper left-hand corner is the big blue 78 for platinum, PT, number 78. That means that every atom of platinum has 78 protons, and every atom with 78 protons is platinum. Those two things sound kind of circular or redundant when in fact they mean sort of two different things. Let's look at that again. Every atom with 78 protons is platinum, and every platinum atom has 78 protons. We're not saying the same thing there twice, right? It's as if we're saying every dog is an animal, which is true, unless you don't count hot dogs or something. But every dog that we think about as a pet is an animal, and every animal is a dog? No, those don't work, right? But we can say that they match each other here. Every atom has 78 protons, and every atom with 78 protons is platinum, and every platinum atom has 78 protons. That's a double kind of redundancy that covers all of our bases on that and makes platinum uniquely 78. You can't be platinum unless you have 78 protons and atomic number 78. And if your atomic number is 78, I know your platinum, no discussion. Okay, so on your periodic table, you'll notice that big blue number is sort of the basis for organization on a periodic table. It goes from number 1 at hydrogen to number 2, 3, 4, 5, up to 118. The periodic table is ordered specifically by increasing atomic number from 1 to 118. More on that and how we got there later. Atomic mass, on the other hand, might be what you guess. Mass, something you've heard about since maybe grade school in some science class, talking about the mass of an object, how much matter an object contains. Okay, it's equal to your size or your overall girth or mass, right? How much you've got for the amount of matter in your body. So if you're a big person, you have a bigger mass. If you're a little jockey, you have a smaller mass. Or if you're just a little kid, you have an even smaller mass. Atomic mass in chemistry is the mass of an atom. And as we talked about on the earlier video, the little table that hopefully you put down in your notes said that protons have a mass of 1 AMU and neutrons have a mass of 1 AMU. Electrons, we said, have a mass of essentially 0 AMUs and therefore are not counted as having any mass at all. Mass of 0. And so as we're defining atomic mass here, it's equal to the number of protons plus the number of neutrons in an atom. Notice the electrons are left out. So simply the number of protons plus the number of neutrons. That's a really simple thing to do. The number of protons in an atom will be a whole number. The number of neutrons in an atom will be a whole number. Add those together and you have the atomic mass. Now it's a little bit simplified. It turns out that atomic mass isn't quite that perfect all the time. But for all intents and purposes, the mass of a specific atom out there in the universe is round about a whole number. And for example, if we had a carbon atom, now if you look at your periodic table, hopefully you'll find carbon there has a big 6 in the corner. Carbon has 6 as its atomic number. Therefore, it has 6 protons. Now, it also happens to have then 6 electrons, because in a neutral atom, the protons and the electrons have to cancel each other out. And a neutral atom is one that has an overall 0 charge. So the protons and electrons cancel each other out. If we have an example, in this example, a carbon atom with 6 protons, with 6 electrons, and with 8 neutrons, what would its atomic mass be? Well, if by definition atomic mass, as you see here, is the number of protons plus the number of neutrons, then you just look at this little sentence I've given you and you take, okay, 6 protons plus 8 neutrons for a total of 14. 14 AMU. Remember, the mass of each of those is measured as 1 AMU. So the total mass would be 6 plus 8, 14 AMUs. Often you'll see an atom like carbon-14 with a mass of 14 written just like that, carbon-14, carbon-14, or carbon-12. For example, here uranium-238, a big heavy mass. All different elements can have all kinds of different masses, anywhere from the lightest atom out there, which is a hydrogen atom, all the way up to the heaviest atoms at the bottom of our periodic table. Uranium is one of those heaviest. In fact, the heaviest naturally occurring element around is uranium. So as we look at an element, we add together protons plus neutrons for any atom at all, and we can come up with its atomic mass and write it just like that. The name of the element dash the mass in AMUs, carbon-14 or just carbon-14, uranium-238, and so on. Now our last kind of new term to go with this then is the isotope. Isotopes are often a word we hear in the common media, often mentioned as something kind of dangerous or unstable or radioactive and so forth. Now there are radioactive isotopes, but certainly not all isotopes are radioactive. In fact, fairly few that you'll come across in everyday stuff will probably be radioactive. And there are plenty of radioactive isotopes all around us every day that aren't harmful really at all. There are plenty that are super dangerous to be around that you wouldn't want to be exposed to, lest you turn into something like the Incredible Hulk or whatever. But the isotopes of our everyday life are not typically radioactive. In fact, you're made of isotopes, all kinds of them. And so what is an isotope? Well, an isotope is defined here as the different atoms of a given element that have a different atomic mass due to various number of neutrons. Now, let's think about that. If I'm a given element, for example, in this case, carbon, we're going to go with carbon on this little chart. Carbon has 3 isotopes. You'll hear me sometimes use the word flavors. It's a kind of a crummy word to use, but it's an easy one that kind of comes out once in a while. Carbon has 3 different isotopes, 3 different forms, or 3 different masses is really all that means. So carbon comes in 3 isotopes, or we can say carbon has 3 different unique masses. And so those masses are due to, as we just talked about, mass is protons plus neutrons. If you add protons and neutrons together, you get atomic mass. And if you can have 3 different masses, as carbon does, the protons have to be the same every time, right? Carbon is number 6 on our periodic table, and so it has to have 6 protons all the time, or it's not carbon. So if protons are always 6, then what's changing? It's got to be the other part of that mass equation, which was what? Hopefully you said neutrons. Carbon is, mass of carbon is protons and neutrons, and that's the same for any element, protons plus neutrons. So the first example of a carbon isotope is given here. An isotope of carbon that contains 6 protons, 6 neutrons, and 6 electrons has a mass of 12 AMUs. Remember the protons plus the neutrons, 6 plus 6. And we would call that carbon-12. Now, there's also an isotope of carbon called carbon-13, which, as you see here, has 6 protons again, because carbon has to, but 7 neutrons. An extra neutron in this form of carbon gives it a slightly larger mass by 1 more AMU, carbon 13. 6 plus 7 protons plus neutrons. 6 plus 7 gives us a carbon 13 mass. And the final form of carbon has 6 protons and 8 neutrons. Now notice I don't make much mention of the other particle here. Electrons sort of get forgotten because in terms of mass they don't make a difference. But 6 plus 8, 6 protons plus 8 neutrons in this example give us a mass of 14 AMUs, or what we would call carbon 14. So those are the 3 different isotopes of carbon. Carbon 12, carbon 13, and carbon 14. Out there in the universe, out there in the world, in your body are many, many carbon atoms. Some of those carbons, most of those carbons, are of a particular mass of this list of 3. Most of the carbons out there in the universe are carbon 12s, and most of your carbons are carbon 12s. But within every living thing, there are also some other carbons because they just naturally show up in the world. There are some carbons in your body that are carbon 14, for example. And so these different masses of isotopes give us a balance or a mixture of carbons and every other element too in the world. And it makes it important that we be able to kind of put all those together to get an overall average mass. If every carbon in the universe was a mass of carbon 12, 6 protons, 6 neutrons, then life would be short and simple on carbon anyway, because every carbon out there would be identically the same. Turns out that that's not the case. We've got a mixture of these 3 out there in the universe. And so we have to be able to figure out then, on the average, what is a typical carbon atom's mass? We can't just say it's 12 because there are other masses to be had. And we'll talk about that with what's called average atomic mass.